So let us look at what we term as enzyme inhibition. We want to look at the different chemicals that can actually alter enzymatic action. That is, they make enzymes not to basically work. So we want to look at how these inhibitors work and what are the implications as far as changing the concentration of the enzyme or changing the concentration of the substrate is concerned in relation to the action of inhibitors. So we start by looking at this scenario. So in this scenario, what we are basically having is that you have a pharmaceutical company that is developing a new drug to manage a problem. This is a rare metabolic disorder that is caused by an excess production of a compound. And that compound is zeta-7. Okay, so we shall call that compound zeta-7. So this disorder, this metabolic disorder, results from overactivity of an enzyme called Z7 synthase. So this enzyme catalyzes the final step of formation of zeta-7. Okay, so we are having in the body, we have a lot of zeta-7, but we have an enzyme that catalyzes the final reaction for forming that zeta-7. Now, to solve the problem, if the scientist can actually inhibit the action of this enzyme, it means that we shall not have this zeta-7. Okay, so what the scientists are actually doing is that they are testing two inhibitors. So one inhibitor, that is inhibitor A, is a molecule that structurally resembles Z7 synthase. Okay, and then the second one, which is inhibitor B, is a large molecule that binds elsewhere on the enzyme and alters the active site. Okay, it does not bind to the active site, but binds somewhere else, but the result is that it changes the active site. Okay, so clinical trials, that is the different, I'm calling them clinical trials, but basically the laboratory trials have shown that inhibitor A is effective in small doses, but becomes less effective when you increase the concentration of the substrate. Okay, but B actually works smoothly or steadily across the different substrate concentration. Okay, though its effects are harder to reverse. So, like again, we said earlier on, in real life, in science especially, we have to make choices. And these choices are actually sometimes very hard to make because you not always have everything on the silver plate. So you have two inhibitors, and you have to choose which one works better. They have different qualities or characteristics. So let us look at the questions. The first question is, can you explain the types of enzyme inhibition exhibited by inhibitor A and inhibitor B? Can you support your answer with diagrams and relevant molecular level details? Okay, can you provide that molecular level detail about enzymatic inhibition illustrated by inhibitors A and B? Secondly, can you compare the effects of competitive and non-competitive inhibition on enzyme kinetics, issues to do with the rates of enzymatic activity in relation to whether competitive or non-competitive inhibition? And then lastly, can you suggest which inhibitor would be appropriate for long-term therapeutic use? Well, using this to treat people who have these illnesses over an extended period of time, especially this chronic metabolic disorder. can you justify your choice using biological and medical reasoning? Okay, which of the two inhibitors can you use to treat this long-term condition? Is it A, is it B, and why? Okay, and then the last point, can you discuss the potential risks associated with prolonged enzyme inhibition in a human body and suggest how this might be monitored or minimized in drug development? Okay, so this is an excellent question. What this question basically hints on are the issues to do with enzymes and how our knowledge of enzyme activity can be actually applied in addressing some of the medical problems that can happen in humans. We already saw that actually enzymatic activity can be applied in managing wastes. And now we are looking at how enzymatic activity can be used in managing certain conditions. Okay, of course, in our bodies, we have metabolic processes that happen. And these processes give us products. Some of these products that come out of the metabolic process are actually dangerous to the human body if they are not reduced to other components, or if they're not broken down to other components that are quite safe. So that means that if people don't have the enzymes that can break these compounds to relatively safe molecules, then they are going to have problems, because these toxic molecules can actually build up in the body, and then you have problems. And for example, just a simple illustration that, for example, if you break down proteins, you get ammonia. And if you don't have the enzymes to convert that ammonia into urea, then you will have problems, right? This is the same thing that we are talking about here when you have a metabolic disorder because of lack of particular enzymes. Or when you have an enzyme that is working very hard and then producing a molecule that will actually turn out to be toxic to the body, then that means that you need to deal with that enzyme and make sure that it doesn't work, such that you reduce the product that it is producing that is actually toxic. So that is the logical reasoning behind this question. Types of inhibition, and we need to relate them to the scenario, whether it is inhibitor A or B, that is competitive or non-competitive. So what we basically need to look for is that if it is competitive, it has to be like the substrate. So in this case, which one looks like the substrate? So inhibitor A is a molecule that structurally resembles the substrate of Z7 synthetase. So that one is competitive. Okay, so here you basically say that inhibitor A is a competitive inhibitor because it resembles the natural substrate for the enzyme, and that enzyme is Z7 synthetase. And then for B, for it does not resemble the substrate and binds on another part apart from the active site to cause the inhibition. So since it does not compete for the active site, it is non-competitive inhibitor. Okay, and that therefore also is shown by their impact, by the impact of substrate concentration on their activity. We actually see from the scenario that inhibitor A is effective in small doses, but becomes less effective when you increase the substrate concentration. So that therefore also points to the fact that it is a competitive inhibitor, because non-competitive inhibitors are not affected by the concentration of the substrate. So part B, effects of competitive and non-competitive inhibition on enzymatic kinetics. And this is about the interaction of these inhibitors with the enzymes. What we basically see is that with the competitive inhibitors, they need to occupy the active sites of the enzymes, okay, for them to cause that inhibition. For non-competitive, they occupy another location apart from the active sites of the enzymes and then cause the inhibition. Okay, so eventually the interpretation is that if you increase the concentration of the substrate for competitive inhibitors, you're making the rate of this enzymatic reaction to decrease, okay, because the enzyme will no longer be active. Not active. The enzyme will no longer be effective because it is not binding to the active site, because the active site is now occupied by the substrates which are in a higher concentration. And then for the other side, increasing the concentration of the substrate does not alter the rate at which this inhibition will happen. So the inhibition by the non-competitive inhibitors will actually happen even when you increase the concentration of the substrate. So that is about the kinetics that are involved. So you explain that in relation to substrate concentration. And then part C, which is about which one could you use for long-term therapeutic use. You need to go back to the scenario and see which one forms irreversible interaction with the enzyme. And that will be the best one to use. So in this case, if you read